Hello everyone, dear professors, dear participants. Today I'm going to present to you my recent work which is entitled Screening of the Most Favorable Metal Oxide Systems for Hydrogen Production via Solar Thermochemical Water Splitting. This presentation will be conducted according to the following plan. Firstly, an introduction, then I will talk about the process of the thermodynamic study that we have carried out. After, I will present to you the results of our study, and I will end with a conclusion. So as you know today, the use of fossil fuels as an energy source presents serious environmental challenges and economic impacts. For that, hydrogen represents a clean energy vector that could efficiently substitute the conventional fossil fuels, and this clean material that can be produced from green sources such as water and solar. So the thermochemical water splitting method is among the promising methods that produce green hydrogen, and this method involves the splitting of water via a repetitive and successive series of chemical reactions. In two-step thermochemical cycles, a low valence mineral oxide is generated through reduction of a higher valence mineral oxide where oxygen is produced. Then the reduced metal oxide reacts with steam during the oxidation reaction, and the hydrogen is generated. So many two-steps water splitting cycles that are based on redox mineral oxides pairs have been studied, and more recently the efforts are directed to the development of materials that reveal low reduction temperature and which have the ability to provide water molecules splitting and have a good cycling stability. So the aim of this study is to make a general screening on different types of materials intended for two-step thermochemical water splitting that are compatible with the operational condition of the concentrated solar power. For that, a theoretical thermodynamic study was carried out to determine the feasibility of redox reactions and investigate the possibility of water splitting using steam or an oxidant reagent to promote the oxidation step. So the thermodynamic study was performed according to these following equations, and which allow to calculate the variation of Gibbs free energy in function of the temperature. I will start with pure metal oxide pair. Among the studied metal oxide, strontium oxide and antimony oxide involves the lowest reduction temperature, 390 degrees Celsius and 840 degrees Celsius. In the case of the oxidation step, the oxidation reaction by water of the studied materials showed the non-feasibility of the water splitting using these metal oxides. Therefore, a stronger oxidation agent such as sodium hydroxide should be substituted for the water. Besides, the oxidation investigation remains only interested in oxidation temperature in the case of antimony oxide, and which is 510 degrees Celsius, and it's the lowest found compared to the oxidation temperature of materials already studied for thermochemical water splitting. For the spinel metal oxides, the results obtained indicate that the thermal reaction for cobalt trioxide occurs at temperature of 980 degrees Celsius, while the reduction of manganese oxide takes place at 870 degrees Celsius. The theoretical oxidation of the reduced cobalt and the manganese oxide is not possible with water. However, when a strong oxidant such as sodium hydroxide is used, this reaction becomes possible, and the results show that oxidation of the reduced cobalt and manganese occurs in temperatures of 600 and 930 degrees Celsius respectively. So to conclude, as I showed you in this study, a thermodynamic study of the redox properties of several types of metal oxides based materials for hydrogen production via two-step thermochemical process has been reported. However, the obtained results figured interesting redox properties of new redox pairs such as antimony and strontium oxides with attractive low reduction temperatures of 830 degrees Celsius and 390 degrees Celsius respectively, and further efforts are needed to improve the potential of these materials for use in the production of hydrogen by the thermochemical water splitting process. And thank you for your attention.